let's talk about the sine function, and once we're done with sine, you'll see where inverse sine comes from. Here on the left, I have the graph of part of the sine function. Okay, notice how this sine function, if I had the whole thing, this would continue forever, right? These cycles repeat forever, okay? Now, I want to find the inverse of this function. And remember when we were looking for inverses and we had a graph, the test we had to do in order to know if the inverse was also a function or not? The horizontal line test. We would do horizontal line test on the function, and that would tell us if its inverse was also a function. So let's do horizontal line test on this function here, sine function. Notice when I do horizontal line test, the horizontal line hits the graph more than once. So we say that this fails the horizontal line test. And if I had more cycles, this horizontal line would hit the graph many, many times. So since this fails the horizontal line test, that tells me that this function's inverse is not a function. Okay, but I want it to be a function. So this is what you do. In order for our inverse to be a function, I'm going to take this function and restrict its domain. And by that, what I mean is we're going to cut parts of this graph off and throw them away. And that is restricting the domain. And what piece are we going to use? We're going to use this piece that goes from negative pi halves all the way to pi halves. Everything after pi halves and everything before negative pi halves, we threw out, okay? So we've restricted our domain. Our domain originally, before cutting these off, was from negative infinity all the way to the infinity. That means all the x values that are on this x-axis, all of them from negative infinity to infinity, were valid for this sine function, okay? Now we're talking about the sine of theta. I like to use theta instead of x, just so you know that this value here corresponds to an angle value. Okay, so on this graph, since it says x, I can change that for theta. Instead of calling it the x-axis, I can call it the theta axis, which corresponds to the x-axis. Okay, so sine of theta equals y, and now the domain, I've restricted it to negative pi halves all the way to pi halves. And notice that the range, which are the y values on this graph, notice the maximum value for this sine function is +1, and the minimum value is -1. So the range goes from -1 to 1. Okay, so there you have your sine function. Before we move on, theta. Theta, this value here, this is your input for this function. And y is your output. Okay, so what that means is you drop in an angle, you take the sine of the angle, and out comes your y, which is your output. And what is y? Y would be your ratio. That would be your ratio. And when I say ratio, I mean a fraction, or it can also be a decimal number, okay? When you use your calculator, you'll usually get a decimal number. When we do values for theta that we know by heart from the unit circle, then y is usually a fraction, okay? When it's values of theta that we don't know memorized from the unit circle, then your calculator will give you an output in decimal form instead of a fraction form. Okay, so for example, if I have sine of pi halves and I look at my graph, I go to where x is equal to pi halves, that's right here, and my graph will hit, or my input will give me an output at this value here, which is 1. Okay, so here's your input, here's your output. Now notice your input is within the range that we said, and your output is also within the range that we said. Well, your input is within the domain that we said, and the output is within the range that we had said. Okay, now for inverse sine functions, like this one here, this is the inverse sine function. That means that I've reflected this piece of the graph across the line y equal to x. And this is how we write inverse sine. We have inverse sine of what? This now becomes y, and this gives you an output of theta. Okay, so now we're working backwards. On this graph, we would say the sine of what angle the sine of this angle equals what? Now I'm saying the inverse sine of this number is equal to what angle? So let's take this same example we have here. If I say the inverse sine of 1 is equal to what angle? To what angle? Okay, so I go on this graph, and now this graph, before we do this example, I want you to notice a couple of things here. Notice that the domain here, look at the domain. That means your x values. Your x values go from -1 to 1. So your domain here for the inverse sine goes from -1 to 1. And your range, look at the range. The range is your y values. It goes from -π/2 all the way to +π/2. So notice how your domain and range switched. The domain and range in the original function and the domain and range in the inverse function are switched. Notice the domain is now the range and the range is now the domain. Okay? So going back to this problem here, the sine inverse of 1, I look for 1. Remember, this 1 is on my x-axis here. When it's 1, what is the angle? There it is. The angle is π/2. So the answer to the sine inverse of 1 is equal to π/2. Okay? So we're doing the reverse operation. Here we're trying to find the ratio, and here we know the ratio. We're trying to find the angle. And this here is your input now. Before, over here, y was your output. Now y is your input. Notice how it's placed where the argument goes. This input here, we can also call this the argument. I didn't mention that before. So now the argument, before your argument was the input in the original sine function, now your argument is what used to be the output in this function is now your input in this one. And your output now is your angle, which used to be your input. So now it's switched, okay? This output, notice, very important for inverse sine, the input, which is your domain, right? Or your valid x-axis values, which are, well, in this case, you would have to write that this is y and this is theta, okay? If you change the label of your axes, your output now is theta and your input is now y. This is just a label. Don't think this is y-axis because it's labeled y. It's still the x-axis, but we've changed the label to a y, okay? Your input, very important, your input can never, ever, ever be a number greater than 1 or less than -1, okay? Because this is the domain that's valid for this inverse function. Any other value is not valid, okay? And for your outputs, which is your range, these outputs can never, ever, ever be values that are greater than π/2 or less than -π/2, okay? So be careful with that. On our next video, we're going to do examples using inverse sine, and you'll see what this means. For now, just keep this in mind. And what we're saying is that we're only going to use, for inverse sine, values that are in between -π/2 and π/2, which is from here to here, okay? this part of the unit circle. But very careful because when we're in the fourth quadrant, we cannot use these values of 11 pi 6 and 7 pi fourths and 5 pi thirds and 3 pi halves. These have to be called differently. This 11 pi 6, instead of saying 11 pi 6, we're going to say negative pi 6. For 7 pi fourths, instead of 7 pi fourths, we're going to say negative pi fourths. For 5 pi thirds, we're going to say negative pi thirds. For 3 pi halves, we're going to say negative pi halves. And why do we do this? Because if you notice, if I ever get an output that equals 11 pi 6, 11 pi 6 is way up here above this value, way up here. It's greater than pi halves, numerically speaking, on this axis. And we said that those values do not exist for the inverse sine. The maximum that the inverse sine reaches is pi halves. Okay, so on our next video, we're going to do examples so you can see what I mean when I say be careful. Okay, I'll see you in the next video.